K. Palanivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on chemistry of environment, and today we are going to look at some of the fundamental aspects of chemistry. First, we will look at what is stoichiometry and how to calculate different reactant amount required for a particular chemical reaction as well as product formed in this particular reaction. So, it is actually deals with calculation of quantities of reactant and products involved in a particular chemical reaction, and it is actually study of relationship between the number of moles of the reactant and product of a particular chemical reaction involved in that. And for this we have to write a chemical reaction equation, that is a stoichiometric equation is actually a short scientific representation of chemical reaction. Apart from this chemical equations, we have to involve the number of moles of reactants involved as well as products formed in a particular chemical reaction. So, it is actually means of expressing what happens when a particular reaction occurs, how the reactants reacted and gets converted into the products. Also, it tells whether what reacts, what is produced, and the relative quantities of each, that is the reactants as well as product based on the stoichiometric chemical equation. And in this chemical equations balance in terms of atoms, that is both right hand side and left hand side should balance. So, chemical reaction including the number of atoms involved should tally. For example, when propane is oxidized with oxygen, it is getting converted into carbon dioxide and water. That is, propane is burnt, we will get carbon dioxide and water. 1 mole of propane will react with actually 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of water. That is, chemical reaction always occur in a integer molar basis always. For example, when carbon is burnt, it forms each 1 mole and carbon dioxide is also 1 mole. So, this means 1 mole of the carbon, that is weighing about 12 gram, react with 1 mole of oxygen weighing about 32 gram to give 1 mole of carbon dioxide, that is actually consisting of 44 gram of carbon dioxide. And all these things we can arrive based on the simple relationship that number of moles is equivalent to mass of the particular substance divided by the molecular weight of the particular component involved in this particular chemical reaction. So, the moles mass and molecular weight is very important, and the basics should be known for calculating any one of the reactants and products. And actually the stoichiometric equation is obeyed by the law of conservation of mass. In this, the total mass of the reactant in a particular chemical reaction equals to the total mass of the products. That is what the law of conservation of mass deals with. That is, matter is neither created nor destroyed in chemical reaction, only it can be converted from one form to another, that is reactant into the products. The key to doing this stoichiometric calculation, which is very important as correctly, is the following steps we have to follow. That is, the relative masses of or the number of moles, the number of atoms or the molecules should be known of the participants in a particular designated chemical reaction. That should remain the same regardless of the overall quantities of reaction participation in a particular chemical reaction. This is very, very important. So, the stoichiometric equations also is concerned by are concerned with a law of conservation of mass. What are the steps actually involved in doing this stoichiometric problem? First one is write the balanced chemical equation for the reaction involved, including the products formed. This is the first step. And then second step is identify the reactant or product whose quantity is known. Okay. For a particular reaction, always we will take known quantity of reactants, okay, or we can monitor the quantity of product formed. This should be known. So, known substance, and one of the whose quantity is being calculated is actually the desired substance. Only one thing is unknown. From that, using this stoichiometric equation we can calculate it. The third step is express the number of moles of the known substance, which usually must be calculated from its mass actually used in a particular chemical reaction. And the fourth step is multiply the number of moles actually involved of a known substance times the mole ratio of desired substance to obtain the number of moles of the particular desired substance. This is a fourth step. And the fifth step is when the molecular mass of the substance are inserted in the particular equation, the equation indicates how many parts of by mass of the reactants react to produce how many parts of the mass of the products. So, the parts by mass are usually in kilogram. So, it is possible to calculate what are the desired mass of the product of for a known mass of the reactant or vice versa. We can calculate basing this. So, these are the 5 steps actually involved in using the stoichiometric chemical equation. So, we will see some small example how we can convert between grams and moles. We know gram is equivalent to moles into gram as mole, that is a molecular weight, and mole as equivalent to gram divided by molecular weight of the substance. Using this, actually we can form a construct a triangle like this. This is a mass, this is a mole, and this is a molecular weight. Molecular weight normally expressed in gram per mole. Okay. Using this triangle, equation triangle consisting of this, that is a relationship between mole, mass and molecular weight, we can calculate any number of actual reactants involved in this. For example, we will see sodium hydroxide, sulfuric acid, sodium chloride and copper if it is involved, how to calculate using this. So, if any one of this out of the 3, 2 is known, we can calculate the third one, that is the logic in this. For example, we know sodium hydroxide, its molecular weight is 40. Okay. Suppose if you want to prepare 0.1 molar sodium hydroxide, what are the weight we have to take per liter can be calculated using this. So, 4 gram of sodium hydroxide, if it dissolve in 1 liter, we will get 0.1 molar solution. Similarly, we know sulfuric acid molecular weight is 98.08, and suppose we take 53.15 gram of sulfuric acid by weight, what will be the concentration we can calculate, and this will be equivalent to 0.5419 mole sulfuric acid. Similarly, salt, sodium chloride, if you take its molecular weight is 58.44. Suppose you want to prepare a 3.55 molar solution, what weight using this equation, this triangle, if you apply, we have to take 207 gram of sodium hydroxide. If we weigh it in 1 liter, we will get 3.55 mole. Similarly, copper pure, metal copper, its molecular weight or atomic weight is 63.55, and if you take 1.27 gram of copper, pure copper, and dissolve it in 1 liter with the help of acid, you will get 0.02 mole. So, using this equation triangle, we can calculate this whatever the concentration based on the molecular weight. It's important thing. Similarly, we can calculate for other things also. So, as I mentioned before, to prepare 0.1 molar, 1 molar sodium hydroxide if you want to prepare, we have to dissolve 40 gram of sodium hydroxide, 1 liter will give you 1 mole of that particular solution. So, suppose you want to prepare standard potassium biiodate, it is one of the primary standard, that is based on the weight actually we can calculate what is the strength of the particular solution. Sodium hydroxide is not a primary standard, in fact it has to be standardized. And for preparing this potassium biiodate, suppose we dissolve 812.4 milligram of potassium biiodate in 1 liter and dilute, we will get 0.0021 molar solution. Okay. So, based on the molecular weight, knowing the what is the nature of this, we can calculate the strength. And but sodium hydroxide based on weight directly we cannot find the strength, because it is not a primary standard. We have to standardize it and find with the primary standard what is the strength of sodium hydroxide. So far we have seen some preparation of some solution. Now in a particular chemical reaction, how we can calculate the amount of reactants or the amount of products formed in this one. For example, gasoline, if it is burned petrol for energy purpose, that is gasoline represented by C8H18 is a hydrocarbon, and if it is burnt with the oxygen, it will form carbon dioxide and water, and we can calculate what is the oxygen requirement to burn this fuel stoichiometrically. For example, so first step we have to write the balanced equation. So gasoline with the oxygen, it forms carbon dioxide and water. If we balance it, this is a balanced equation. So based on this stoichiometric equation, which indicates 1 mole of this gasoline equivalent to 114 gram of this fuel, which reacts with 12.5 moles of oxygen, that is equivalent to 400 gram of oxygen, to form 8 moles. Actually that is equivalent to 352 gram of carbon dioxide and 9 moles of water. So 9 into 18, that is equivalent to 162 gram of water will be formed in this equation based on this. And we can calculate also the oxygen to fuel ratio, because in this, as per this stoichiometric equation, oxygen requirement is 400 gram divided by the fuel based on the molecular weight is 114. So the ratio comes to 3.51. Okay. And this is called usually stoichiometric ratio of the combustion system. So like this, any fuel of known molecular weight we can calculate accordingly. Suppose we take 100 gram of the above one, how much of carbon dioxide will be formed? We can calculate based on this stoichiometric ratio or based on the chemical equation. So 114 gasoline divided by 352, that is equivalent to 100 gram into so many gram of carbon dioxide. So what is the amount of carbon dioxide? By putting all those things we can calculate. Actually 100 gram will liberate 308 gram of carbon dioxide, whereas 114 gram will liberate 400 gram as per this previous one. So based on this stoichiometric equations, we can calculate what is the carbon dioxide liberated into the atmosphere or what is the oxygen required based on the stoichiometric equation we can work out. So these are the some of the important stoichiometry where industrial operation that process hundreds of thousands of chemicals per day, pharmaceutical industry, other industry, they do lot of synthesis. In all these things we should know what are the amount required as per the stoichiometric equation, because all the chemicals also costly. So the economics of the particular industry depends on this. We should not waste chemical also, that becomes leads to waste material, because only stoichiometric amount is incorporated into the final product, remaining things goes as a waste. So we should not employ excessive reagents or reactants also. So obtaining accurate values in chemical analysis, which need to be known to withstand what part per thousand are often involved highly exacting stoichiometric calculation also in chemical industry. So, this is important in terms of chemical industry as a reagent to minimize the economics, from environmental angle to minimize the waste also. This is very, very important, especially for wastewater treatment. Normally we express the concentration in milligram per liter or ppm, and sometimes very rarely molarity solution. Okay. There is a relationship between this milligram per liter or ppm. For aqueous solution it is same, whereas for air pollutants it is different, and the molarity relationship here we should know. So, milligram per liter is equivalent to molarity, normally expressed in moles per liter, into molecular weight of the particular chemical substance, normally expressed in gram per mole, into 10 power 3. That is a conversion from milligram to gram. If you know this relationship between the ppm and the molarity of the relations, we can find other calculations of environmental importance. Theoretical oxygen demand is one of the very, very important in terms of wastewater treatment, all those things, because they represents the organic matter, and we use to express normally in terms of COD or BOD, that is chemical oxygen demand and biological oxygen demand. In this also the stoichiometry play a very important role. We will take a model example of glucose and how to calculate the theoretical oxygen demand, which is relevant to BOD and COD in wastewater. We know the molecular formula of glucose is C6H12O6 and molecular weight is 180. So, suppose glucose is oxidized either chemically or biologically, oxygen should be present, and that is converted into 6 moles of carbon dioxide and 6 moles of water. So, 1 mole of glucose reacts with 6 moles of oxygen to form 6 moles of carbon dioxide thing. And if you put all the molecular weight oxygen, so 6 times into 32, that is equivalent to 192, carbon dioxide 44 into 6 244, and water 108. So, as per this stoichiometric equation, we can see 180 gram of glucose requires 192 gram of oxygen in terms of moles. Okay. Suppose we take a glucose concentration of 1.67 into 10 power minus mole of glucose, that is actually represented as 300 milligram per liter. As per the previous equation, we can, putting the molecular weight of glucose, we can arrive at this value. You can see here. So, 1.67 into 10 power minus 3 moles of glucose is equivalent to 300 milligram per liter. And based on this stoichiometric one, we can calculate for this 300 milligram per liter, the theoretical oxygen demand we can calculate it 300 into 192, that is the oxygen as per the stoichiometric equation, divided by 180, that is the molecular weight of glucose, that is equivalent to 320 gram. So, 320 milligram per liter of oxygen is required to oxidize completely all the glucose into carbon dioxide and water. So, this is very, very significant to know the BOD and COD value of a wastewater, and that is arrived based on the theoretical oxygen demand for this. And in real wastewater, if you look at it, the BOD value will be somewhat less than the theoretical oxygen value, because some of the amount of original organic carbon is incorporated into bacterial cell tissue. That is, a bacteriological organism will take some part of this carbon into their biological cell, and as a result what happens is the amount of theoretical oxygen value is reduced, because carbon is converted into the living biomass. So, because of this reason, we always get the BOD value less than the theoretical oxygen demand. This is one of the important things we should remember. Another example, how to calculate the chemical demand requirement for a particular chemical reaction, with another example is chrome reduction. The wastewater industry, especially electroplating, and all, hexavalent chromium will be present. This hexavalent chromium is one of the highly toxic material. In fact, chromium in normal samples may present in two oxidation state, +6 and +3. +6 is highly toxic chromium, whereas less toxic is trivalent chromium. And most of the industries like electroplating, they use hexavalent chromium. As a result, the wastewater comes out from this industry will be toxic hexavalent chromium. This treatment is very, very important in the field of environmental issues, especially containing chromium. And this chromium is removed in industries by two-step process. Usually, the first step is reducing the hexavalent chromium to trivalent chromium, and then precipitate the trivalent chromium as an insoluble chromium hydroxide and removed from the wastewater. Okay. So, what happens is, for reducing the chromium is important. First step, and then raise or adjust the pH to near neutral 6 to 8, chromium hydroxide will be formed as an insoluble precipitate that is removed. So, very important step is reducing or converting the hexavalent chromium into trivalent chromium, and this is accomplished by variety of reducing agent in slightly acidic medium. For example, sodium metabisulfite is one of the important chemical used in industries. Other things are, even iron is used, even ascorbic acid, many other reducing agents are employed for this purpose. Okay. So, here we all know potassium dichromate is a powerful oxidizing agent. So, it will react with this reducing agent sodium metabisulfite in a slightly acidic condition and get reduced to trivalent chromium. At the same time, the sulphite will be oxidized to sulphate under this condition. Okay. So, this is a reaction actually involved. What is the amount of sodium metabisulfite required to convert this hexavalent chromium into trivalent chromium as per the stoichiometric equation? Okay. So, 1 mole of dichromate actually consisting of 2 parts of chromium, that we have to bear in mind, and 3 moles of bicarbonate is required for each mole of dichromate. If you work out the chemical requirement, that is sodium metabisulfite for this chromium reduction, let us take a small example and see. Let us assume the effluent from an electroplating industry containing 52 milligram per liter of hexavalent chromium, and the dissolved oxygen content of the water also 5 milligram per liter, and the industry discharges about 150 meter cube per day of effluent. So, this is what actually happening. Now, we have to calculate what is the amount of sodium metabisulfite required for managing this effluent, which consisting of chromium plus dissolved oxygen also present. This will also consume sodium metabisulfite. So, as per the previous stoichiometric equation, 3 moles of metabisulfite, that is 104 gram molecular weight, to reduce 2 moles of chromium, that is 52, atomic weight of chromium is 52. So, 312 gram of sodium metabisulfite is needed to reduce 104 gram of chromium, that is 3 gram of sodium metabisulfite for 1 gram of chromium as per this above stoichiometric equation. So, hexavalent chromium to be reduced as 52 gram of chromium per meter cube, and that actually volume is 150 meter cube per day is released. Okay. So, that will be works out to be 7,800 gram of chromium is per day. That is actually equivalent to 3 times of this value, 7,800, that is actually equivalent to 24.3 kilogram per day of sodium metabisulfite is needed only to reduce the hexavalent chromium to trivalent. And suppose we assume the commercial grade quantity is 0.5 kg per liter, then the solution required is 46.8 liter of sodium metabisulfate, 0.5 gram per liter is to be dosed to reduce this. But unfortunately, the wastewater also contained dissolved oxygen, that has to be also taken care, otherwise the reduction of hexavalent to trivalent may not be complete. So, we have to calculate the amount required for eliminating the dissolved oxygen also. So, if you write the stoichiometric equation, sulphite will be oxidized by oxygen to sulphate or sulfuric acid, and as per this equation 6.5 gram of sodium metabisulfate is required for 1 gram of oxygen. So, 5 milligram into meter cube, that is also contains 150 meter cube per day. If you work out, it comes to 750 gram has to be dosed to reduce the oxygen itself. So, or in other words 750 into 6.5, that is equivalent to 4.9 kg per day of sodium metabisulfate. This is required to eliminate the dissolved oxygen present in the system. Okay. So, what is required is you have to write the stoichiometric equation, and based on the incorporating the molecular weight or the atomic weight of the substance, we have to calculate what is the thing. So, the total sodium metabisulfate requirement for this industry of that above particular combination works out to, this is 23.4 for chromium alone, and this 4.9 is for dissolved oxygen incidentally present in the particular effluent. So, totally we have to provide 28.3 kg of sodium metabisulfate per day of this particular industry, which is discharging effluent containing 52 milligram per liter of chromium, which has incidentally also 5 milligram per liter of DO, and the effluent quantity is 150 meter cube per day is the actual amount required. So, like this we can calculate the various type of things, not only the aqueous solution, even for air pollutants we can calculate the chemical released, all those things based on the stoichiometric. So, this is one of the very important fundamental things we should, what we have learned in school, how to apply for this environmental aspects in calculating. For example, in the industries, in the synthesis, what is the amount of reagents employed, we should know based on the stoichiometric. That is very important, not only in terms of economics, from pollution angle. If you provide more reagents, definitely it is going to end up with the waste. There is another headache for the industries. So, always we have to calculate what is theoretically needed and what is really required for the particular synthesis, and not wasting chemical, that is important. The other aspect is we know what are the amount of products in chemical reactions. Always not only the products, the byproducts also will be formed, that is also very important. That also we can calculate what are the amount of the waste formed or the byproduct formed, that we can recover or we can do something. And ultimately any industries, when we go for wastewater treatment, as I explained a case with the chromium, similarly we can calculate the chemical requirement involved in various wastewater treatment also. So, in all these aspects, what is important is the basic stoichiometry, what are the real chemical reactions involved, and what is the number of moles, and what are the products we are getting out of it, and what are the waste ultimately is thrown out into the environment. That is has to be paid attention. Thank you.